We left off yesterday with looking at John Snow's thematic map of the cholera outbreak of 1854 in London, and that's considered one of the most significant thematic maps in modern history in that it immediately served a very important human purpose, stopping a disease epidemic. So that's one of those early examples of how spatial information can be very, very useful. So this first section I call mapping discrete data, and essentially we're going to look at what we call dot maps and isopleth maps. Dot maps represent what we call discrete data. Discrete data are just observations of individual phenomena. To understand what discrete data are, you kind of have to know what normalized data are, which is the next section. But for now, hopefully it'll become apparent. Discrete data can be represented in several ways over space. But what we want to do here is to visualize a distribution's pattern and density and anything that we can tell from it. So there are a couple of subtypes of dot maps. There are really two subtypes. So I want you to be able to know the difference between these two types of dot maps. There are what we call dot distribution maps, and this is the ideal type of dot map where every item on the map is actually located correctly with perhaps a latitude and longitude coordinate. So the data points should contain an absolute location. What we mean by absolute location is essentially this, a latitude and longitude coordinate on the surface of the Earth. So the absolute location is something that is basically your GPS coordinate, all right, or your set of GPS coordinates. In contrast to absolute location, you will run into the term relative location, all right? And the relative location this refers to the location within the context of a place. So this is the more important facet of location. Specific location or absolute location and relative location. I'll give you an example. Stillwater can be described, or OSU can be described as having, a GPS coordinate. If you were to assign this campus one point, what would it be? Well, you would probably want to identify a location like Whitehurst or the Student Union or something like that, a nodal point. Doesn't really matter. But it can have that absolute location, or it can have a boundary. It can be considered a polygon on the map. On the other hand, if you wanted to describe Oklahoma State University's campus relative to other things, you would probably describe it as an hour north. Remember time-space compression or time-space ideas. An hour north of Oklahoma City or an hour west of Tulsa, something like that, relatively speaking. I'll give you another example. This works for us, all over the place. If you were traveling around Oklahoma, and let's say you're out driving around, you stop and have lunch, you meet somebody, and they ask you where you're from, okay? And let's say you're from Tulsa, or let's say you're from Catoosa, all right? You know where Catoosa is, west of or east of Tulsa, and so you would tell this person, well, I'm from Catoosa, and they would say, oh, I'm from Enid. Okay, I know where Catoosa is, just east of Tulsa, right? So you go on about your merry way. But what if you're traveling in Argentina? Or what if you're traveling in, let's say you're traveling in New Hampshire, and you stop and have lunch, and you meet somebody from New Hampshire, and they ask you where you're from. Are you going to say Catoosa? No. You're going to say, I'm from Oklahoma, right? Because you assume that they're probably going to know where Oklahoma is, but probably not Catoosa. And likewise, if you're traveling in Spain or Germany, do you suppose you're going to say, I'm from Catoosa, right? No, they'll probably ask you where you're from, and or they'll probably assume you're from the United States, and they might ask you where you're from in the United States, and you would probably say, I'm from Oklahoma. I'm from, the south central part of the United States, if they don't know where Oklahoma is. So relative location is very important in our just day-to-day communication. Okay, so there are two types of dot maps. One's a dot distribution map. If we were to map, say, the hometowns of everyone in the classroom, then we would have hopefully a pretty good idea of the locations of all of those hometowns, or maybe even addresses on the map, depending on the scale of the map. So that would be a dot distribution map, where every data point is actually the absolute location, where it is actually on the ground. In contrast, the dot density map is sort of like what we'll see in what's called a choropleth map. The dot density map is one in which the dots are symbolic of observations of phenomena, but they are randomly distributed across an aerial unit. All right? And this is important because dot maps can serve more than one purpose. They can be used for discrete data, but they can also be used to map normalized data. The two types of data we're talking about today. Discrete data, that's individual observations, or normalized data in the sense of a ratio or a percentage.
Dot maps are pretty flexible. We can use dot maps to show discrete data, individual observations, as well as data that are aggregated or normalized to individual aerial units. That would mean things like data that are associated with, let's say, the counties of the state of Oklahoma. If we were to look at something like an election return, we might find that 30% of voters in Payne County voted for a measure or a candidate, and 70% of voters in Caddo County voted for this same candidate. So that variation is associated with the aerial units, in this case the counties of the state. And while a choropleth map is usually ideal for that, we can also do it with a dot density map to indicate in a visual way gradations of density or gradations of volume, whatever. So it's often used in agricultural maps put out by the USDA. So any questions about the dot distribution versus dot density? Dot density is aggregated within an aerial unit of some type. Another aerial unit would be something like the states within the United States, countries within the world, precincts within a city. So anything that has a boundary that acts as a functional region is what we're referring to. Any aggregated, or a census tract is a great example of an aerial unit. Okay, so for the most part, dot maps, at least the dot distribution maps, are really not that great for normalized data, but the dot density map can be used and often is used for that. So it's not really intended for it, but it's not really hard and fast rules necessarily. All right, so let's look at the some examples here. I'll try to give you some reasons why you sort of should and shouldn't use these. This is a map that portrays, anybody guess what this is? Multiple phenomena. I guess you can see the key down here in the lower left part of this slide. The map is indicative of earthquakes up until about 2014 in Oklahoma. You might know that Oklahoma experienced a period when we had a number of tremors, of small earthquakes, small shallow earthquakes that started up about 2008, 2009 and lasted into, 2015, 2016. We still have a few every now and then, but back in 2013, 2014, we were having all kinds of earthquakes. And, you know, we're not really here to discuss the reasons for that, but we kind of know why. The phenomena that are being mapped in this case are assumed to have some relationships. If you look at the yellow dots indicate all of the earthquakes recorded between the years 1974 and 2008. And this, again, this is one of those maps. Remember, I said, why did they put, you know, color coding on this map? This is a base map that's not that great. We shouldn't have probably done that. But the distributions I want you to look at, first of all, the yellow dots. The yellow dots are the tremors that occurred over that period from 1974 to 2008. Very, you know, fairly long time span, 34 years, right? So 34 years, you don't have that many. But then if we look at the red dots, 2009 to 2014, only 5 years, versus 35 years, you have this clustering of earthquakes, particularly in north central and northwestern Oklahoma and a few elsewhere. And then if we look at the distribution of things like saltwater disposal wells, that's where brine from the oil and gas extraction industries are deposited because it's an EPA-based, you know, EPA considered hazardous waste, and those, you know, the fluid from these wells is fluid from the production process that's transported to these old wells and deposited in these older wells. And then we also have injection wells that are from that are more recent, that are injection wells of effluent from the hydraulic fracturing process. And so there are lots and lots of these disposal wells located. But essentially what I want you to look at is each one of these red dots and all of the items on this map are actual locations of those phenomena. So this is a dot what? Distribution or dot density map? I'm asking. It's the first one, a dot distribution map. So the dot distribution is significant in that you want to look for, okay, well, there's clustering that's going on here and that sort of thing. So that's a dot distribution. That's the appropriate way to use a dot distribution map. You're wanting to identify associations, aerial association between locations, discrete locations. An isopleth map, okay? I'm not going to show you a dot density map here because it's not the ideal way to map it. Just wanted to make sure that you do that. The isopleth map, on the other hand, is a way of mapping what we refer to as continuous data. So I mentioned discrete data, I mentioned aggregated or normalized data. There's also something called continuous data, and any sort of continuous data is something that just varies, well, smoothly over space. But what matters is that every location has, for the most part, every location has a measurement, a potential measurement. Now, if we were to measure temperature in this room, so we have a very, very sensitive thermometer that could measure air temperature throughout different locations in this room and across three-dimensional space. There are variations in the air temperature. Of course, air temperature above your body is going to be a little bit warmer than perhaps the surrounding air. But measuring that sensing or measuring that temperature variation would be kind of difficult, wouldn't it? Because we don't have the ability to measure every possible location. So we have to do something called interpolate. We have to interpolate data. And that means that we have to assume, we have to basically sample the distribution. Right? So any type of data that exists out in space but you can't possibly measure every point. We usually assume to be a continuous type of data. What are some other examples? Can you think of any? Continuous data, something that exists out there that could be mapped in a discrete way, theoretically, if you had an ability to do so, but it would perhaps make a lot more sense to map a sample of it here and there in order to get an idea of its distribution. Excuse me? Tide? Yes. In a fluid, for example, if you're looking at oceans and water temperature, water volume or height, density, all sorts of ways. There are all sorts of measures that we could. Salinity, okay, are some examples from like ocean or lake water, and so we would, since every point on that water body has a variable, has a temperature or something, we would want to exactly. That would be a good way to do it. So anything that's fluid, like air is gaseous, but it's a fluid. Anything that's fluid and changes a lot is often mapped with something called an isopleth map. Good. Other examples. How about things like property values? Property values across space. Property values tend to change a little bit with whatever is existing on the surface. And that's going to change a little bit, but things like what landlords charge for rent are going to be fairly standardized based on things like square footage, right? Or perhaps what property owners charge businesses for their office space, or anything like that. And depending on location, you're going to have variations in value, variations in price and rent, and so that's something that would certainly be possible to map with an isopleth map. Generally, it tends to be more physical geography stuff. So isopleths, or the isopleth itself, is a line that connects, or a line that indicates a constant. So an isopleth is a line on a map that indicates equal measure of something. We looked at the contour lines on a topographic map last time. So elevation is a type of isopleth itself. So the contour lines connect areas of equal elevation. Remember that? So that's an example of an isopleth type map. But it can also be things like temperature. We would call those isotherms. Barometric pressure we would call isobars. Rainfall we would call isohyates, contour lines, etc. So the line connects a point in space of continuous equal value, and to draw those lines we have to interpolate. That is, we have to topologically space the distribution of the line. Now it can be done by hand, looking at a distribution, a field of data, but it's not so easy. It takes some practice. However, computers can do it like that, no problem at all, and be much more accurate than human beings. So this allows the visualization of spatial gradients. We saw that with the topographic map when the contour lines are since the contour interval is all the same, when the contour lines get farther and farther apart, what happens to the slope or the gradient? The gradient gets shallower or smaller. And when the lines get closer together, okay, when the contour lines or isohyates or whatever come closer together, there's a greater gradient or slope in the case of contour lines. Okay? So there's more distance, there's more change over space. Okay? So perhaps some examples here. We've seen this, right? So where are the flatter areas? The flatter the flatter areas on this topographic map would be right about here where the slope is less, and the very, very steep slopes would be where the contour lines are very, very close together. So this allows visualization of in this case, slope, but it could also mean things like density. In this case, we have a map of air temperature across North America, and you can say, you can probably guess this is during the wintertime, right? So this is January 17th, 2012, and we have a cold front, probably an Arctic front, sliding down out of northern Canada into the mountain states and the Great Plains. But here in Oklahoma, in January, can you imagine the temperature where we are in Stillwater would have been what? About, what is that, about between 50 and 55 degrees, okay? But just traveling up to a little past Woodward into the Panhandle, and the temperature drops down below freezing, okay, pretty quickly. So this is a very steep temperature gradient between this dense cold air moving south and east, and this warmer, lighter air down here in the south, closer to the Gulf of Mexico. And if you look right here in East Texas and Louisiana, there's not much difference at all between the temperature. It's between 65 and 70 degrees. So 65 to 70 degrees, and it's pretty much evenly distributed throughout this area. But the temperature gradient is much higher here. Now, where would you expect to have high winds at the surface? You would, if you looked at this map, you would say the winds are blowing really, really strongly in Oklahoma at the moment, because this is temperature, but it could also be implied to a certain degree as barometric pressure. So what you're looking at is very high barometric pressure here and lower barometric pressure here, and air wants to flow as a fluid. It wants to flow from higher pressure to lower pressure. So this is an Arctic blast hitting Oklahoma in January for the most part. Down here in Louisiana and Texas, no wind, lots of wind here. Okay, not so much wind up here because it's just a big high pressure air mass.